the honor of presenting right before lunch. So thanks for bearing with me. We'll give this a shot. So we're going to now venture from the upper atmosphere of Pluto down into its interior. And we're not only going to restrict ourselves to Pluto, but we're also going to include many of its other friends from the Kuiper Belt. So it should be fun, hopefully. This slide basically gets at the motivating question for what I'm going to talk about. It's actually not going to be very much review. So I'm sorry to the organizers that it's going to be a lot of new work that I've been doing. And this question is the crux of what we normally focus on in the solar system when we're not searching for life. It's to ask ourselves, well, we see something, what part of that can be attributed to formation versus evolution? And this can be a really tricky question, especially when we have more limited data in the Kuiper Belt. This is what you'd call the vintage view, right? We don't call anything old, it's all vintage. And the idea is that these bodies were originally thought they could be like giant comets, right? That had been preserved in a deep freeze way out there in the solar system's third zone. And that was kind of the prevailing view, I think, in the 1980s and 90s. If you look at a lot of papers, that seems to be the sentiment, is that we could learn about the solar nebula from studying Pluto and Triton and these other objects. But then we started to get more data, right? And we start, especially at New Horizons, we learned that these bodies are more active. At least at the surface, we see that Jeff Moore and Oliver showed that there's active geology that's going on today on Pluto. We've also learned that there's interesting photochemistry and escape. So it's not so simple as them just being giant comets that have been frozen relics. Something's been happening. But this is still the view of these objects from just surface processes. These are still, we think these processes must be happening. But then now what I'm going to do is I'm going to introduce the possibility of, if you have these energy sources on these bodies in the interior, like James King was talking about, what kinds of chemistry might those interior sources of energy drive? The first hint of some mischief on some of these KBOs was actually obtained in the late 1980s by Voyager 2, by the UVS experiment, when they were looking at solar occultations of Triton's atmosphere. And they found that the atmosphere is dominated by N2, molecular nitrogen, and there's not much carbon monoxide. And this is really puzzling because comets are loaded with carbon monoxide. So something was unusual and unexpected. And in the early 90s, then when high-resolution ground-based astronomy started to kick off, we also learned that the surface ices of both Triton and Pluto are really depleted in carbon monoxide. So again, some funny business was going on. And this just reemphasizes this point. Not only is carbon monoxide really abundant in comets, but it's actually really hard to find N2. So Pluto and Triton looked very different from comets, which directly flies in the face of this idea of them being giant comets, right? But one other process that might explain this would be hydrothermal processes in the deep interior. And let me show you how this works. I'm glad that Bill kind of alluded to this in his talk. Him and Everett Schock, my PhD advisor, built on this notion of a hydrothermally active Triton that was introduced by Dave Stevenson in the early 90s. And the idea is we think that based on its orbital properties, Triton is a captured KBO. And during the capture process, it would have originally started with a high eccentricity around Neptune, but now its eccentricity is very low. So the process of getting a low eccentricity would lead to tidal heating, very fierce tidal heating in Triton's interior that in fact could melt all the ice like Bill's talking about and even the rock, and you could have a pulse of very intense internal heating. This just shows a calculation from Schock and McKinnon. There it is, okay. And these were just very simplified models showing how you could have phenomenal amounts of heat flow from Triton's interior. I added something that's more recent. This is Enceladus's global heat flow. It's about 30 milliwatts per square meters. It just barely falls on this plot. Here's Earth's average. You can see for these different models of Triton, the amounts of internal heating are insane, right? And so then they proposed, Bill and Everett proposed, that you could have some kind of analog of hydrothermal activity on a seafloor on Triton, where you could have hot water circulating through rocks, and that might drive some very interesting chemistry that could explain things like the missing CO. Here's a diagram. This shows a plot of the stability fields of CO and CO2. So CO is above this dotted line shown right here. And then this solid curve corresponds to what's known as a phaolite magnetite quartz buffer. It's kind of a proxy for what rocks provide for the oxidation state as the temperature starts ramping up. And you can see that if you follow a rock buffer, you're always in the CO2 regime, which means that there's a huge thermic drive to convert CO to CO2. And that's what this paper was all about. More recently, we found also that other Kuiper belt objects are remarkably deficient in CO. These are data that were acquired from the James Webb Space Telescope during Cycle 1 GTO. This is a paper by Will Grundy from 2024. These show the spectra along with Hapke model fits, and I've also conveniently pointed out where CO would be shown. So you can see these faint features here. That's a model for what you would see if CO were present on the order of a part per million by volume. Those dips are not observed. So it looks like CO is less than 1 ppm V abundance on these Kuiper belt objects, Eris and Makemake. You'll also notice, while we don't see CO, we see these huge features corresponding to deuterated methane. So that allowed the deuterium to hydrogen ratio to be calculated about 2 to 4 times 10 to the minus 4. These are roughly moderate values that are actually pretty similar, a little bit elevated compared to Earth's seawater. And this provided a great opportunity for us to try to answer some questions about where the methane that coats these bodies came from on Eris and Makemake. Here's how we think about the origin of methane. You can have 3 main categories of methane: primordial, abiotic, or thermogenic. And the simple way to think about them, primordial would be like the direct inheritance of methane from the solar nebula, right? You can think of it like cometary type methane. Abiotic, we call it abiotic, but you can kind of think of how geochemistry could make methane from CO2 or CO through some kind of hydrothermal process involving hot water and rocks. And then thermogenic derives its name from how methane is produced from the cracking of complex organics when we form natural gas and oil on Earth. And Bill talked about how you could have an organic rich rock that could produce methane and other types of volatiles. The beauty of having these new data on the D/H ratios, we can actually now start to use data to test some of these sources. That's what we did here. This summarizes quite a bit of modeling, but you can check out this paper that I published last year in Icarus. And what I'm showing in this plot is the D/H ratio for different models compared to the data from Eris and Makemake. And right away, if you compare the data to the models, you see that the cometary type primordial methane doesn't fit, right? You look at what you'd expect for cometary methane, the D/H ratio is expected to be quite high, unlike what we found on Eris and Makemake. So it appears that that's not supported, whereas the abiotic hydrothermal scenario or thermogenic scenarios can reproduce the observed D/H ratio. I'm going to focus in on the hydrothermal or abiotic case in the last part of my talk because it offers the potential to both explain the moderate D/H ratio and the missing CO all in one type of model. And to do this, we're going to now return back to Triton and Pluto. One observation that was mentioned in a question that Bill addressed was Triton is extremely rich in CO2 ice. It appears to be the most CO2 rich object as far as ice in the solar system. And Ian Wong will have a talk, I think, on Wednesday on this. There's a clear contrast with Pluto. CO2 is very scarce on Pluto. And this was first found in 1993, and then New Horizons also never found conclusive evidence of CO2 on Pluto. So you can kind of boil it down to, in real simple terms, that Triton appears to have a very high CO2 to methane ratio. Pluto appears to be low. This may reflect differences in hydrothermal processes. Kathy Mont had a paper a couple years ago that introduced this as a hypothesis. And so what we're going to try to do here is model this to some degree and see what we could potentially explain. Here's how we do it. I think I'm going to skip the slide. Nope, no, I guess not. Okay, so what I did here is I developed a model of hydrothermal speciation, and this builds on a model that I first published. This is actually my first paper from 2008 on Enceladus. We were looking at CO2 to methane ratios in the plume on Enceladus. And now we're going to apply this to Pluto and Triton. This is a better version of that model because I've actually gotten a little bit better, I guess, since 2008. And we're going to be looking at temperature and redox like I did there, but also expanding to other important geochemical factors like the pH, which is how acidic the water is, non-ideal chemistry of ions, charge balance. This is a more comprehensive model. It has a database that's going to be tailored to large KBO seafloors. I've tried to make best estimates of parameter ranges, and these are performed using the GeoChemist Workbench software. This is just to kind of ease you all into how we're going to think about how geochemistry can work inside a large KBO. So this is a plot, again, showing like the stability regions, like Schock and McKinnon did earlier. This is at constant temperature of 200 degrees Celsius. This is pH with respect to neutral. So 0 is pH neutral, and then you go alkaline, positive, acidic is negative. This variable on the vertical axis is how oxidized or reduced the system is. So hydrogen is a reduced molecule. You have more hydrogen, it's going to be more reduced. You can see as you walk around this diagram, if you're up here, lots of hydrogen, you should make lots of methane, right? Go down here, you have CO2. The conditions get more alkaline, then you get carbonates like bicarbonate or carbonate. I've estimated for KBO conditions, probably they're going to be somewhere around this pink region. So you'd expect at this temperature, 200 C, that you'd have a lot of methane. And then this shows an example for the nitrogen system. It's actually pretty similar as far as you get a lot of ammonia. So that's a reduced form, but you can have ammonium if the fluid is weakly acidic. So it's a little bit different. And then I've also developed other approaches. So I'm calculating in the previous slide the volatile ratios in a hydrothermal fluid. The question is, what actually gets to the surface? And so you can imagine that that's like step one here. Then we got to kind of understand if you have a hydrothermal fluid that gets dumped into an ocean, how you're going to have some kind of respeciation in cold ocean water. And then if you're going to erupt stuff on the surface, you got to account for another fractionation step where you could form some kind of, let's say, a cryovolcanic plume. Turns out that, again, Enceladus could help us here. I had a paper just a few weeks ago, actually, that attempted to develop a model of how you could relate the volatile composition of ocean water to the plume composition. This works pretty well on Enceladus, so I thought, well, why don't we apply this to Pluto and Triton and see what we can actually predict? So that's what I did. So I'm going to walk you through very quickly a few results here. So what I'm going to calculate is a CO2 to methane ratio that would be predicted on the surfaces of hyperbelt objects like Pluto and Triton. The main variable here is how oxidized or reduced the system is. This is versus the Baolite magnetite quartz buffer. So Pluto or Triton should be near 0. And now these are the first sets of results. This is at 200 degrees Celsius. And these are different pH cases. So this is neutral pH. This is neutral +3, so this would be alkaline. What's interesting is that you actually cannot get valid solutions at acidic conditions. So you can see that you can generate models, and once you get here, you stop because equilibrium favors ammonia. And it turns out that if you go to these really reduced conditions, you get too much ammonia, and the system wants to make ammonium when it's acidic pH, and there's actually not enough anions in these systems. Chloride is not very abundant in chondritic rock, so you can't actually charge balance a cometary abundance of ammonia and convert it all into ammonium. So you stop there. If it's alkaline, you go all the way and turn all your nitrogen into ammonia. This line here shows where CO2 and methane equal one another. So you can see as you get more reduced, the CO2 to methane ratio will decrease. You get more methane, right? And then these just show various other cases at intermediate pHs between neutral and neutral +3. Just to fill in the parameter space. These are my current best estimates for Triton and Pluto CO2 to methane ratios. I think these are fairly poorly understood, but the main message is, based on the observations, that Triton should be many orders of magnitude higher in CO2 to methane ratio than Pluto is. And so you can see in this particular illustration, you could intersect the Pluto observation at 200 degrees Celsius at a redox state that we might consider reasonable for Pluto's rock. In contrast, to explain Triton, you can't really intercept it at 200 degrees C, but if you boost the temperature up to 400 degrees C, then you can generate a new set of model curves here, and now you can actually intersect the Triton region. So this may be an indication, a hint, that Triton has experienced more pervasive, strong hydrothermal conditions, i.e. higher temperature conditions in its rock. And this may be attributed to that early phase of tidal heating, the very powerful tidal heating that Triton might have experienced after its capture by Neptune as eccentricity were gradually dampened. And so this is my final slide here, just showing a conceptual picture of what might be going on inside of Triton as the illustration. Pluto, I think, may be kind of similar, but a more mellow version of Triton. So Pluto is a mellow Triton where you didn't get the insane amount of tidal heating in the interior. And I'm still working on, looking at what this means for nitrogen and Eris and Maki-Maki. They're very methane rich. CO2 hasn't been found there, so they may look more similar to Pluto than Triton. And ultimately, this is a hypothesis. I think there's some intriguing consistencies right now, but I really want to advocate for a new mission to Triton so we can test this picture and see how much of this picture might actually carry forward to the present day. And with that, I think I'll let everyone go to lunch. Thanks.
Okay, we have 7 minutes for questions. So
Oh, plenty of time.
yeah. If we
Hey, Chris, that's great. I'm really glad you were able to answer Tanguy's question.
Yes, we did not coordinate that at all.
Okay. I was asking whether you had thought of even something more extreme, like you take Triton and you actually melt the silicates. I mean, you basically have a blast furnace. You have graphite, you have rock, you have tremendous production of CO2, which is vented and then reduces the core, but all that CO2 ends up on the surface.
I have not done that yet. I think, so you could have graphite being converted to CO2 on Triton, I think. I don't know if graphite could persist because the plot that you showed from the book chapter, graphite really prevails at the reduced conditions. Then once you switch over to more oxidized, the carbon wants to go to CO2. I guess you could have a scenario where Triton gets oxidized, its carbon goes to CO2 mainly. Pluto stays in the reduced state with methane and graphite. That could work.